So, hello, I'm Robin. I'm going to present our work on implementing confidential Byzantine fault tolerance services using our proposed COBRA framework. So to implement fault tolerance services, we can use the state machine replication model. This model allows to implement practical systems such as blockchains by replicating the execution of the service into multiple machines in such a way that even if some of them are Byzantine, the availability and the integrity of the service is maintained. In this model, the servers maintain the same state and they deterministically execute the same sequence of operation in this state, producing the same resulting state. However, since all the servers have the same state, even if an adversary compromises even a single machine, he can read all the data stored in the system. So this model does not provide any guarantees about the confidentiality of the stored data. So how can we preserve the confidentiality in a model where the data is replicated across replicas? In this work, we explore the secret sharing mechanism. In this mechanism, a client called dealer divides the secret into multiple pieces called shares and distributes them among the servers called shareholders. And the client with proper access, when wants to retrieve the secret, he can read a subset of those shares from the servers, combine them and reconstruct the secret. To implement this mechanism in practice, we use the Samir scheme because the share size in this scheme does not depend on the number of servers nor the number of faults tolerated by the system. Without going into detail, in this scheme, the secret is encoded in a random polynomial and the shares are computed as a point in this polynomial, as shown in this example. And this scheme ensures that revelation of up to t shares reveals nothing about the secret, and to recover the secret, client can combine at least t plus 1 shares. This way, if t servers are compromised in this model, the availability of the service is not compromised and the confidentiality of the data is maintained. However, implementing Samir scheme in practice, is not enough to implement practical system because first, in this scheme, shareholders and combiners do not have any means to verify the validity of the shares. For example, a client that wants to retrieve the data uses a share compromised by an adversary or even by accident, he will obtain the wrong secret. The second problem is that shareholders in this scheme do not have any mechanism to recover their shares without the client redistributing the secret. And the third problem is that in a long-lived system, a mobile adversary, given enough time, will be able to compromise the minimum number of servers and their shares needed to reconstruct the secret. So the typical solution for the first problem, add additional information in form of commitment that allows shareholders and combiners to verify the validity of the shares, thus building verifiable secret sharing schemes. The solution for the second problem adds a protocol that allows shareholders to blind their share before sending them to the recovering server. And the solution for the second problem is another protocol that allows servers to periodically recompute their shares without reconstructing the secret. And the resulting scheme of last two protocols is called proactive secret sharing scheme, which was later extended to support dynamism, where it is possible to move secret shares from one group of servers to another without reconstructing the secret. So the contribution of this work is a dynamic proactive secret sharing scheme called COBRA, which is a modular protocol stack that enables recovery of the servers, reconfiguration of the system, while supporting thousands of secrets stored in the system. And we believe that recovery, reconfiguration, and handling of many secrets are fundamental features needed in a practical system, because existing systems that integrate secret sharing do not have all these required features implemented in the same system. So for the first time, we integrate a COBRA dynamic proactive secret sharing scheme into fully featured replication library called BFT SMR that has all the required features in practice, such as recovery and reconfiguration, making it the first practical library that we know of that supports implementation of services that require confidentiality of the stored data. So among the existing proactive secret sharing schemes that support dynamism in a non-synchronous model, COBRA allows reconfiguration of fault tolerated in the system without requiring storage of extra information during reconfiguration. It also has a linear share and combine complexity. It has a cubic reshare complexity, and the servers only require the storage of information in servers only requires constant size. So we assume a standard dynamic system model where the system evolves in a sequence of views, and each view are installed using reconfiguration. And in each view, there are T Byzantine replicas that can fail simultaneously. And we assume that clients are prone to Byzantine failures, and we assume partially synchronous model. So with the integration of secret sharing, instead of all servers having the same state, now each server state is composed of two parts. First, it's a common state, which is same in all servers, for example, ID of the data. And the second part is the private state, which is composed of the shares of the confidential data, which is different in all servers. And the system as a whole stores the same state as the system without confidentiality. And in this extended model, we guarantee the secrecy property, which is stated informally as an adversary learns no information about the confidential data if the data is not accessible by the faulty client and the adversary controls no more than T servers. So next I will present our protocol, but you can find all the details in our paper. So our work integrates three secret sharing protocols into the SMR replication model. The first protocol, which is the recovery protocol, that allows servers to rebuild their private state with the help of other servers. A dynamic resharing protocol allows to reconfigure the system and protect it against mobile adversaries. And both recovery and resharing protocol use the distributed polynomial generation to create random polynomials used to blind the private state during the state transfer. However, implementing polynomial generation in distributed and in the non-synchronous model is challenging. To explain why it is challenging, at first let me explain how the polynomials are created. To create polynomials, each server locally generates a random polynomial and they exchange the shares on these polynomials. So in the end of this second phase, phase of the exchanging shares, each server will obtain the shares on the local polynomials of the other servers. And an elected leader selects a set of T+1 local random polynomials that are valid for him and proposes that set in the consensus. During consensus, servers verify using the commitments if the shares that they have received on the proposed polynomials are valid for them or not. If the majority of the servers agree that their shares are valid, the output of the consensus is the set of shares of the polynomial selected by the leader. So the final polynomial is the sum of the polynomials selected during consensus. But in practice, each server will add their shares of the polynomial selected during consensus. So in the end, they can verify using commitment that the shares that I have received on the final random polynomials are correct or not. However, in the adversarial setting and in the non-synchronous model, during the share exchange, a malicious adversary can send valid point to majority of servers and invalid point to other remaining servers. So when during consensus a leader selects a polynomial of the malicious server and since the majority of them received valid share on these polynomials, the consensus will finish with the polynomial of the malicious. So when they add these shares of the selected polynomial, the protocol can only guarantee that at least T+1 honest servers will receive valid share because majority of the servers have agreed during consensus, but at most T honest servers will receive invalid shares, which they can verify using commitments. So the key insight of COBRA is that we can, forgot to say that only with this information, we can use the recovery protocol because with honest server with T+1 valid shares are enough to use recovery protocol. But this is a problem during resharing because honest servers that have received invalid points, they cannot finish resharing their private state. So the key insight of COBRA is that we can leverage the recovery protocol to recover the points on the random polynomials after removing malicious servers. So to remove malicious server, the honest server that received the invalid point pinpoints the local invalid polynomial in the set selected during consensus and accuses those senders of those local polynomials by sending an accusation to the other servers. If the accusation is valid, all the honest server will add these faulty servers into an ignore list, and then the honest server, to recover its point on the random polynomial, can use the recovery protocol. Since in the system there are at most 3 faulty servers, eventually the honest servers will remove those malicious servers using this accusation phase and recover its point on the random polynomial. So using this protocol as base, during recovery, a recovering server asks the blinded state from other servers. Those servers generate random polynomials and use it to blind their shares before sending it to the recovering server. The recovering server collects and combines at least T+1 blinded share to reconstruct its share of the secret. To reshare the private state within the same group or to move secret share from one group to another, servers in both groups create 2 random polynomials. Servers in the old group use one random polynomial to blind their private state before sending it to the servers in the new group. The servers in the new group collect and combine at least T+1 blinded shares and use the other polynomials to compute the reshared private state. So we have implemented this, the COBRA protocol into the BFT SMR replication library, and we also, to compare with the existing approach, we implemented VSSR and MPSCS, and you can find all of these implementations in our repository. And to measure the impact of integrating secret sharing into the replicated model, we implemented a simple confidential key value store. Here you can see that during the write operation, the integration of the secret sharing has a higher cost when we write confidential data, because we can see that COBRA's throughput drops significantly compared with the system without confidentiality. The main reason is that during the write operation, servers have to verify the shares, because when we turn off this verification, the throughput more than doubles. However, it's still halved compared to the system without confidentiality, because in our experiment, we noticed that the throughput was limited by the network bandwidth. But when we compared with the VSSR, which is the state-of-the-art protocol for recovery that sends pre-computed information for recovery during write operation, we can see that COBRA can process more than 3.5 times more transactions per second. During recovery of the 100,000 secret shares, we can see that recovery of the private state adds additional cost compared to the system without confidentiality. Nevertheless, COBRA can recover 1.5 times faster than the VSSR, even though VSSR has pre-computed information. And to reshare 100,000 secret shares, we can see that COBRA can reshare 5 times faster than the state-of-the-art protocol MPSCS. The main reason is that in COBRA, we only require only require 2 random polynomials to reshare a secret, in opposite to the MPSCS that requires n+1 random polynomials. Here we can see that impact of removing malicious server during resharing has negligible cost in a system with large number of secrets, because the cost is diluted across the resharing of multiple secrets. So in this work, we propose a COBRA framework, which is a practical confidentiality framework for BFT SMR. The proposed protocol has minimal storage overhead and base communication complexity among the existing proactive secret protocol in non-synchronous model, and the COBRA protocols are significantly faster than the existing approach in practice. Thank you for your attention.
Excellent presentation. Any questions from the audience? Oh,
Hi, thanks for the talk. I'm Saurav from UIUC. So what's your threat model? Like, do you consider T failures including in the both group, or in if total T failures if we combine the failures in both the groups, or total two T failures?
We tolerate 2 T failures during resharing.
I see.
Yeah.
Then I think in the previous protocols I have seen that you need a degree 2t resharing, right? The generation of the random polynomial must have degree 2t polynomial.
This protocol doesn't require much. There are other protocols. I think it's Sharp that exchange the degree of the polynomial during the state transfer. But protocols like MPSS and our, they don't require to increase the degree of the polynomial, and still they can handle 2t malicious faults.
I see. Okay, thanks.
This is more of a clarification question, but so suppose there is an initial share and then a committee reconstructed and then they shared again and then a committee again reconstructs the shares. So in the middle process, when someone before resharing, if they change the message to be reshared, like after collecting it, can you also detect this in the later committee, and if so, how?
I don't know if I understood your question.
It is like I share my shares, right?
Okay.
And then like people collect them, and there is a malicious node who, after collecting things and combining them, before resharing, it changes the message.
If you are asking me if the shares are modified?
Yeah.
If they are modified, the servers can detect using commitments, and they just don't use that modified shares.
The commitment is from the before the previous share, right?
If the secret is the same,
Oh, okay.
During
I
the
see.
write of the secret, they also write the commitments.
Okay, thanks.
No more questions? Okay, let's thank the speaker again.
Thank you.